So just to finish off with, just going to look at some different graphs that have appeared over the years. Let's have a look at this one. Here's the random graph they gave us. It actually looks like a reciprocal of a parabola, because that's the sort of shape you get for that. But anyway, the ones they wanted us to draw that particular year. The first one was the reciprocal graph of this. So this actually looks like the reciprocal of a parabola, so we should probably end up with a parabola when you think about it logically. Right, let's go through the important points. So they've told me that turning point's at 2. So 1, as we've seen, is an important point to know where that is. So using the scale they've given me, I can work out, okay, one's about there. Now remember, when you turn an asymptote upside down, you don't get an x-intercept, you actually get a point discontinuity at those points. So I'll put those in. And as far as x-intercepts, well, this didn't have any to turn upside down. So turn -1 upside down, it stays at -1. Turn 2 upside down, it becomes a half. That's pretty much it. So there we go. Well, it's got that U shape of some sort of parabolic function there. Okay, so where the original graph was increasing, this one's decreasing, and all those sorts of things. So that was the first graph they asked us to draw. This one's a little bit more interesting. Draw function x plus the absolute value of function x. So we've got the original graph, and we're going to add to it the absolute value. So I guess we need to work out what the absolute value one looks like. So we find the absolute value, whatever's below, reflected above. So these two hyperbolic branches would get reflected, well, and I've stretched them a bit to go up to the top of the asymptote there and above. And of course the U shape would be identical. So I'm now adding the blue and the black graph together. So in between the two asymptotes, well, that's easy enough, it's just going to be twice all those y values. Here's where the big mistake was made. What happens when you add these two together, the two hyperbolic branches? Right, it becomes 0. But what a lot of people said was, oh, that's positive, that's negative, add them together, they'll disappear. And drew nothing. Okay. So what actually happens, well, let's first of all add the turning point together. 2 and 2 is 4. So there's in the middle. So you basically get the x-axis, and it'll be a point discontinuity where the asymptote originally was. But as I say, a lot of people left off the x-axis part. Let's square the graph. Square the graph. A little bit boring, this one, because there's no x-intercepts to actually turn into turning points and things like that. What can we do? Well, we can square 2 and get 4. We know that when we square -1, we'll get +1. Well, there's the middle section. So again, we'll get a higher U shape, because every y value is squared there. Well, basically, we'll just get it sort of looks like it's reflected, but of course every y value is actually squared there. Here's something we haven't really looked at. The other sort of graph that they might ask us to draw is e to the power of function x, or log of function x, or inverse tan of function. But one of our functions, where the angle or the power or whatever we're talking about is function x. So how to handle something like this? Probably the first thing I do when I'm doing this is to the side, I draw myself the basic curve. So I've got an idea of what the important features are. So to the side here, I'd go, okay, well, look, they're asking me to draw e to the power of something. Now I know when I draw it, e to the power of x does that. It cuts at 1. So key points I'm then looking for is, I know that when the power of 0, it goes to 1. So over here, what do we say? We're saying when the function value is 0, it goes to 1. Now in this case, it never goes to 0. However, there is a horizontal asymptote there at y equals 0. So my new horizontal asymptote will be e to the power of 0, 1. So I know that's going to be a horizontal asymptote. Other key things. I know as x approaches infinity, so does my curve. So what I'm saying here is when my y value approaches infinity, this curve will approach infinity. When the x value approaches negative infinity on the original curve, we're approaching 0. So over here, when the y value, so down here, approaches negative infinity, that's going to be approaching 0. So we're going to get a point discontinuity here. Because when it comes down to a particular value, we're going to get a point discontinuity. Okay. Sometimes helps to look at the derivative as well. So it gives a feel for what's going to happen at stationary points, things like that. So my new curve has a derivative of f dash x e to the function x. So I know that stationary point will remain a stationary point. Obviously the y value will change. And also when e to function x equals 0, well, e to the function x will never equal 0. So I know they won't create any new stationary points. Okay. Let's have a look. So my turning point goes to e squared. So e to the y value. So e squared. Again, in between those two asymptotes, we've just got some sort of U shape. Okay. So we're going to have point discontinuities there. Horizontal asymptote we said was going to y equals 1. So it's got to come out of this point and go asymptotic to this curve. There's two things it could do. It could either, okay, so let's see. Here's the point. There's the asymptote. It could just come out like that. That would probably be what most people would put, because it seems the logical thing. But of course, the other thing it could theoretically do, it could inflect. Now, how can I tell the difference between those two? And how I can tell the difference is the slope. Because as we're going into that point discontinuity, the first one, the one on top there, has a steep slope, whereas the one below has a shallow slope. So if I investigate the derivative around that point, so that was when as x approaches the value of 1, which meant the y value was approaching. We've got to be careful here. So the x value approaches 1. The derivative of the original graph times the y value of the original graph. That's what we're basically saying there. Because it's f dash x times a function x. So if I look at the original graph, the derivative, as we're getting closer to that point of discontinuity, is getting closer and closer to negative infinity. So something negative very large. But then we have e to the function x. And so the y value is also approaching negative infinity. Well, that would imply it's not that. Hang on. Did I sub in wrong? Let's look at that again. The original point, it's e to the function x. That was my mistake. I substituted in the y value of the original one, not e to the y value. So let's try that again. F dash x, so that is the original derivative. The original derivative, when we look at around 1, is negative infinity. It's increasing. Yeah, you're right. Okay, so positive infinity. Whereas the other one would be negative infinity. That one's going down. Okay. So we now want to look at the new y value, don't we? Because it's e to the function x. We're going to multiply that by the new y value. The new y value is approaching 0. I've got infinity times 0. How do I work that out? That's where the idea of dominance comes in. What's going to dominate? The exponential curve will always dominate. The exponential was going towards 0. Therefore, this derivative would be going to 0. Yep. So that's why it's the one that inflects rather than the one that just comes out. Would they have penalised? Again, it's probably one of those ones where it's only worth a couple of marks. There are lots of different things, obviously, you have to put on there. Possibly they may not penalise if you miss that out. But technically, that should inflect there. All right, let's have a look at this one. 2002. So this was their random graph that particular year. Again, they've given us an idea of where 1 is for scale. So that's going to help us out. Reciprocal, they want us to draw. So same as the last one, started off with reciprocal as well. Okay, but this time I do have some x-intercepts. So x-intercepts will turn into asymptotes. So now I have asymptotes there. When I turn -1 upside down, it'll be -1. And when I turn +1, it'll be +1. I'm just for the sake of it, assuming this sort of ended at -1 there, but obviously it would continue through to -1 eventually there. I've had a bit of a look at when is it positive, when is it negative. So I know the sign doesn't change, but what I do know is when the original graph was below 1, it goes above 1, and when it's above 1, it goes below 1, and all those sorts of ideas. So that's what I've shaded in there. So I know the regions they're going to shade into. Okay, so there's my picture, because I know I've got to go bend towards that asymptote. The x-axis becomes a horizontal asymptote because the original graph's going off to infinity. So therefore, when I turn upside down, the new graph's going off towards 0. So there it is. There's the reciprocal graph. Next one, y² equals function x. Well, that's the same as saying y equals plus or minus the square root of function x. So we do the square root of function x first and then reflect it. So this is where it becomes really boring, this particular graph, because anything below no longer exists for our purposes. Yeah, well, oh, that was oh, look, I've got a little branch there. Okay, I just need to find the square root of that. Don't forget about that point. There was the big mistake everyone made. There is a single point at the origin, because the square root of 0 is 0. It still exists. The rest of it was below. Okay, so there's a single point there. Now for the other bits. So I know square root of 1 is 1 and 0. What's it going to look like? Well, probably one of those ones with a vertical tangent. Try to draw it. How well I draw it will depend. Now we'll see how good the reflection is. It'll look nice and straight, like a circle, you know, vertical tangent, if I've done it well. I said if. Obviously it shouldn't bow in like that. But. So there's our graph. Oh, no, we'll move on. Okay. So absolute value of function absolute value x. So in this one, I'll do function absolute value x first, and then I'll say, right, let's do the absolute value of that particular graph. Function absolute value x, well, that's one where we're saying we're only substituting in positive numbers. So the left-hand side of the y-axis will disappear. So left-hand side disappears. Whatever's on the right will reflect over to the left. There we go. And now, so that's y equals function absolute value x. Now I'm going to take the absolute value of that. So whatever is below will be reflected above. Well, whoops, that was close. So something like that. The log of function x. So yeah, the first thing I would do is I'll draw myself up a log curve. So I get a feel for what the important points are. So we're saying log of function x. So whatever the y values are of this original curve, we're going to find the log of it. Look at our graph there, the log graph. Can't find the log of a negative number. It doesn't say the log of the absolute value of function x. It simply says log of function x. So again, a lot of this graph becomes boring because I can't find the log of a negative number. So that's no longer in my original graph. And in this case, that single point's not included because you can't find the log of 0 either. Oh well, goodbye. Okay, let's have a look at this last little section. I've drawn in a vertical asymptote this time because if I look at my log graph at 0, I have a vertical asymptote. So I know there's going to be a vertical asymptote there. I guess the other key point there is where the y value is 1. And the log of 1 is 0. So that'll become an x-intercept. So now I've got an x-intercept there. It's basically just going to be a log curve now because we're saying to the left-hand side of that x-intercept, it's going to be a log of a number that's less than 1. Well, look at our graph. Log of a number less than 1. Yeah, okay, it's that part of the log curve. And on the right-hand side, it's going to be log of a number greater than 1. Well, we're going to have the rest of the log curve there. So we some sort of log curve for that bit. Okay.